So let's move into Reynolds transport. Here's the kind of theoretical expression that is Reynolds transport theorem. And I should mention here, this Reynolds is the same as the Reynolds number Reynolds. So Osborne Reynolds, that's who this equation is named after. This is not the Reynolds number, however. The Reynolds transport theorem does not tell you anything about whether the fluid is laminar or turbulent. What it does tell you is how a fluid system that you define interacts with the surrounding environment by basically exchanging intensive and extensive properties with the surrounding environment. And the way that I like to think of it, I think the best analogy is to think of the Reynolds transport theorem equation as like a bank account, right? So this first term on the left, the time derivative of B of the system, B, by the way, is some extensive property of the system. So something like the mass, the momentum, the energy, all of those are extensive properties. That term on the far left is like the rate of change of money in your individual checking account, right? So you define what the system is. It's your checking account, and that's the rate of change of money in your checking account, that term on the left. This term here in the middle on the right side of the equal sign, this term represents the total amount of money accumulation in the bank, right? So not just your checking account, but in the overall system and structure that is the bank. So the time rate of change of that money accumulation in the overall institution. And then this last term on the far right, this is the flux of money into and out of your bank account. So if you go to the ATM and you deposit a check, that's a flux of money into your bank account. Notice that it's both going into your bank account and into the bank simultaneously, right? So it's going to have an effect on both of these terms. If you go to that ATM machine and you pull cash out, that is an extraction of money from your bank account. And so this term just keeps track of basically the money going in and the money going out of your particular bank account. CV stands for control volume. That's the region through which the system passes during a process. So you can think of it again as your checking account sort of sitting inside the bank. But the bank is the overall control volume. And the control surface, CS, that's the surface across which whatever this extensive property is that you're tracking, that's the surface across which that property is passing, right? So for the money analogy, it's the ATM machine or the bank teller, or if you do direct deposit, your direct deposit system, it's the money crossing the system boundary is the control surface, the surface across which that happens. Okay, this is all very theoretical. The best way I think to explain Reynolds transport theorem is to actually give a concrete example. And so here's an example, mass conservation, which you guys know very well, right? You guys have been doing mass conservation since you were freshmen. This is something that would come up in physics 1 or even high school physics. So the equation for mass conservation that you know is the one that I've got boxed here down in yellow at the bottom. So let me explain how we get from the theoretical Reynolds transport theorem down to the equation that you guys know, which is the change of mass of the system with respect to time is equal to the sum of the mass in minus the sum of the mass out. So we need to select the extensive property that we're tracking. In our case, because this is mass conservation, the extensive property is mass. So B in this case, which again, remember B is the amount of the extensive property in the system, we're just going to make that M, the mass of the system. And unless you're a nuclear engineer, once you've set the mass of the system, that mass doesn't change, right? Mass cannot be created or destroyed. If you're, again, a nuclear engineer, yes, it can, because E equals MC squared. But for our purposes as mechanical engineers, once you set the mass of the system, that mass is fixed. So the change of mass of the system that you've set with respect to time, which is the term on the left, that must be 0, right? Because mass can't be created or destroyed. We next need to figure out what the intensive version of mass is. And you guys hopefully remember from your thermo class that you can take any extensive property and convert it into an intensive property by dividing by mass, right? So volume is an extensive property, density is an intensive property. The relationship between volume and density is a division by mass. And so because our extensive property is mass and we're dividing by mass to get to the intensive property of mass is 1. This is actually kind of a funny thermo piece of trivia that I talk about when I teach thermo, is the extensive or the intensive mass of every object in every system in the universe is the same. It's all 1. So because you're just taking the mass and dividing by mass to get to 1. So in our case, we're going to, for lowercase b, which is again that intensive property equivalent of the extensive property in Reynolds transport theorem, we're going to drop the value 1 in here, and we're going to drop the value 1 in here, and then we're going to carry out these integrals and figure out what they actually represent, remembering that the term on the far left-hand side of the equation is 0 because the mass of the system is fixed. So what we end up with is that the accumulation of mass in the control volume with respect to time, that's the middle term, is equal to the total sum of the mass that we put into the system minus the total sum of the mass that we take out of the system. That's what comes out of the term on the far right-hand side of the equation. So that's how we use Reynolds transport to get from kind of this weird esoteric theoretical expression to the mass conservation expression that you guys know. Can I answer any questions about that? Good so far. Okay, let's move on to momentum conservation. So I'm going to do the exact same thing, except now instead of tracking mass as my extensive property, I'm tracking momentum as my extensive property. Momentum goes as m times v. So that's capital B is my extensive property, n times v. The key thing here for momentum conservation is to remember Newton's second law, right? Newton's second law tells us that force equals mass times acceleration. What is mass times acceleration? Well, it's really just the derivative with respect to time of momentum, right? The time derivative of m times v is m times a because mass doesn't change. So, and we'll come back to that in a second. The intensive property of momentum is just m times v divided by m, which is just v, the velocity that we're tracking across the system boundary. So we put our extensive linear momentum in on the left side of the equation. We put our intensive linear momentum here for v and here for v on the right-hand side of the equation. And then we have to interpret what all this stuff means. And so for the left-hand side of the equation, again, we're taking the time derivative of the momentum. So Newton's second law, F equals ma, tells us that the time derivative of m times v is m times a, which is the total force on the system. So that term on the left is just all the force acting on the system. The terms on the right, this term here is the time rate of change of the intensive momentum inside the system. For our purposes, we'll just set that to 0. It's a complicated expression that in most cases ends up being 0. So we don't have to worry too much about that in most cases. The term on the far left here, this is the momentum flux across the system boundary. So this v dot n dA, when I integrate that across the control surface times the density, that works out to just be the mass crossing the system boundary at this particular velocity. And so we end up with the sum of the forces on the system are equal to the flux of momentum entering the system minus the flux of momentum leaving the system. And that's it. And so the way to really think about this equation is to think about like a gas turbine engine, a jet engine on an airplane. So you know from thermo that the fluid cannot enter the compressor at sonic velocity, right? The flow has to enter the compressor subsonic. Otherwise, you surge the compressor and your jet engine doesn't work anymore. So the fluid is entering at a relatively low velocity, but the fluid then enters the gas turbine. It goes through a combustion process. The pressure increases, the volume increases, and that fluid gets pushed out the back of the jet much, much faster than it entered. So the momentum entering the jet is relatively small. The momentum leaving the jet is relatively big. And the net result is a force of thrust produced by the jet engine that keeps the airplane flying forward. So that's probably the easiest system to think about is a gas turbine engine. It's small momentum flux in minus large momentum flux out gives you a net force that causes the airplane to continue moving forward against the force of drag. Okay, questions? Yeah.
Does the bar over the V, that indicates an extensive property, right?
The bar over the V is a vector.
Okay, okay.
Yeah. So these continue to be vector quantities because force is a vector. So you have to keep track of the direction of the velocity, the vector direction of the velocity to make sure that you end up with the correct vector direction of the force.
Okay.
I have a question too.
Yep.
How do you distinguish between volume and velocity? Is capital V volume, or like I've seen volume with a slash through it. Like, so just to be sure, this is mass times velocity because momentum, right?
Yeah. So at least in my notation, I use in my notation I use capital V as velocity, and if it's the vector, I put a bar over it, and I use a V with a slash through it as volume. Capital V with
Okay.
a slash is volume, and if I need to distinguish an extensive property from an intensive property, the extensive property is capitalized, and the intensive property is lowercase.
Okay, thank you.
Yep. All right. Any last questions? All right, so let's move on. I am not going to solve Reynolds transport theorem for energy conservation because it is a mess and it is almost totally useless, particularly with fluids that are compressible or fluids that have viscosity, which is all fluids. You end up with an energy generation term and you cannot solve for that energy generation term. And so energy conservation Reynolds transport theorem is not useful for anything practical. So I won't deride that for you, but what I will tell you is with the right assumptions, you can turn the Reynolds transport energy conservation equation into Bernoulli's equation, which is more useful. And so here is Bernoulli's equation, but you have to be very careful with Bernoulli because there are 4 key assumptions that must be true for Bernoulli to apply. So 1 is that the flow is in steady state. 2 is that the fluid is incompressible, again, because of that compressibility term in the energy equation. 3 is that the flow is inviscid, right? Because viscosity is an energy loss mechanism. So if I combine 2 and 3, that gives me assumption number 4, which is the big one, which is that this is a flow that has no energy losses. And provided I can get away with assuming that I have no energy losses, which in the practical terms of the Reynolds transport theorem means that that energy generation term is just very small compared to the other terms in the equation, then I can use Bernoulli and it's relatively accurate. But this is like the key pitfall in fluids is people really like Bernoulli because it's sort of fun and easy to use. And you'll end up feeling like you want to apply it in situations where you cannot make this assumption of no energy losses. And so that's a problem that students usually, a trap that students usually fall into, is trying to apply Bernoulli in situations where it cannot be applied. For example, pressure loss down a pipe. That's Darcy-Weisbach. That takes into account the viscosity of the fluid, and that's empirical. So provided Bernoulli is correct and we can assume no energy losses, it's a really simple equation that just relates the pressure energy to the kinetic energy, the pressure energy, the kinetic energy, and the potential energy at one point in a fluid streamline to the pressure energy, the kinetic energy, and the potential energy at another point on a streamline. And the beauty of it is that because there's no energy loss, Bernoulli just shows you how those energies move from kinetic to potential to pressure and vice versa. And so here's a classic example where we have a venturi, which is a contracting or a converging diverging nozzle. And if we follow a streamline where the cross-sectional area is high, the fluid flow velocity is relatively low. And then the fluid has to speed up for it all to get through that contraction at the neck of the venturi. And because the fluid is going faster at station 2 than it was going at station 1, we're effectively trading kinetic energy for pressure energy. And so the pressure at state 2 drops below the pressure at state 1, and you get the expression that P1 is greater than P2 as a result of this exchange between the kinetic energy and the pressure energy in the flow along a streamline, which is super useful for all kinds of flow metering and sort of predicting what the velocity and the pressure are going to be at various places in a flow field, provided the flow field doesn't have any significant energy losses.
I would always get confused with the incompressible fluid. Does that mean that the volume is constant?
It means that the density is constant.
The density is constant?
Yep.
Okay.
Constant density is incompressible fluid. Yep. Other questions while we're here? Okay, sorry, I'm just racing because I've got 2 minutes left and I want to show you guys this burette behind me before we run out of time. Okay, the last element of Reynolds transport is hydrostatics. So if I take hydrostatics, by the way, static means it's not moving, right? So if I take Bernoulli's equation and I eliminate the velocity terms, then I get the hydrostatic equation, which is here, right? So, and all the hydrostatic equation does is just tell you the pressure as a function of the depth in a stationary static fluid. And the interesting thing about hydrostatics is it doesn't matter where you are in terms of like the shape of the fluid around you, so long as you are at a constant depth in a continuous fluid, the pressure is always the same. So it doesn't matter that lowercase a, lowercase b, lowercase c, and lowercase d are all sitting in kind of regions of this fluid that are surrounded by different shapes. The pressure at all of those stations is all the same because they're at the same depth. By the same token, uppercase A, uppercase B, and uppercase C are all at the same pressure. They're at a greater pressure than the lowercase letters, but they are all at the same pressure relative to each other, again, because they are all at the same depth. Station D is different because D is in mercury, and so we have a discontinuity between the liquid water and the liquid mercury, and so D is going to experience a higher hydrostatic pressure, capital D, a higher hydrostatic pressure than capital A, capital B, and capital C, and that's because there's a discontinuity in the fluid there. Okay, we're not going to use manometry, so I'm going to just skip over this slide, but you can use manometry you can use hydrostatics to calculate pressure differences or pressures in fluids. I don't think it's going to be relevant to the burette, so I'll skip over this and get to the last slide in the last 30 seconds of class, which is an example reverse engineering report fluids analysis. So even though you guys don't have the burettes and the stopcocks in hand yet, you guys can already start thinking about the types of analysis that you want to do for the 3 fluids analysis, the 3 dynamics analyses, the 3 Mech 1 analyses, and the 3 DML analyses. And the one that I think is super interesting, because we can actually run the experiment and you can compare your model to the experiment, is to ask the question, how fast does the burette drain? And the way that I would solve this problem is I would make the Bernoulli assumption, and I would create a streamline between station 1, which is at the top of the fluid, and station 2, which is at the bottom. And the fluid is sitting now in the burette, and it has a height of L. And we're going to set the bottom of the burette, basically where the stopcock is, at z equals 0, and we're going to count upwards from there. So if I apply Bernoulli along this streamline, I open the stopcock and the fluid starts moving. I know that the pressure at 1 and the pressure at 2 are the same because the stopcock is open and this is a jet, so it's jetting out into the atmosphere. And so the pressure at that point is going to be atmospheric pressure because we have pressure across a jet. We also know that Z2 is 0 because we set Z equals 0 at station 2. So those 3 terms go away. And if I rearrange things, I'm left with this equation, which is 2GL equals V2 squared minus V1 squared. And L, by the way, is going to be a function of time, right? As the fluid drains out of the burette, the height of the fluid is going to drop. So I'm going to keep L as a function of time. From the conservation of mass, I know that any mass that leaves the system at station 2 has to be accounted for at station 1. So that allows me to equate the velocity at station 2 to the velocity at station 1 multiplied by a ratio of the area. So this is the cross-sectional area of the burette and the cross-sectional area of the stopcock. And if I rearrange things, I end up with an expression that has L on one side and only V1 on the other side. But remember, V1 is dl dt, right? Because this fluid is moving and the velocity at which it's moving is just the rate of change of L with respect to time. So if I take V1 equals dl dt and I plug it into this expression, I get that guy. And I can now solve this for dl dt, and it's a differential equation that has L as a function of time on one side and dl dt on the other side. So I'll leave it up to you guys to kind of solve this guy and figure out what L as a function of time is. But once you get L as a function of time, then all you have to do is determine for when L equals 0, how much time has elapsed. And that's the amount of time that it took to drain the burette. So questions about that derivation?
So that was essentially 1/2 mv squared, like the kinetic energy, but just in terms of density, pressure, and gravity.
Sorry, over here?
Yeah, right there in
This
the
guy.
two. Mm-hmm.
Yeah, right. So maybe a way of thinking of it is I'm trading, in a way I'm trading kinetic energy for potential energy. Yeah, because this side of the equation has all the kinetic energy and this side has all the potential energy, and I'm trading one for the other. Yeah, that's a good way of thinking about it.
Thank you. Dang, I wish you were my fluids professor.
Oh no. No, I'm sure whoever you had did a great job. It feels easy because it's all review, I'm sure. Okay, and I'm sensitive to the time. I'm recognizing now that we're a couple minutes over. So I did want to show you the experiment. So let's quickly do that, and then we'll wrap up. So let me just pin my video. And let me make this big so that I can see it. Okay. And I figured out that this actually works the best, weirdly, when I have all the lights turned off. I don't know why that is, but let me get out of the way. Turn off all the lights. Okay, so what you guys are seeing is a burette that I filled up with basically water that's colored red so that it's easy to see. I have a stopcock here at the bottom that's turned off. And interestingly, this is sitting on top of a scale. This scale is set up to log data as a function of time. So I'm actually going to be able to give you guys data. I'll collect the data and share it on Canvas for how much mass is leaving the burette as a function of time. And you will be able to compare that to the theory that we just walked through how to derive and how to solve for, and tell me how good, Bernoulli's equation is at predicting the drain rate of water from a burette. Before I turn the stopcock, any predictions about whether it's going to be faster in the beginning or slower in the beginning than it is towards the end?
Faster in the beginning?
Yes, it's faster in the beginning. And why is that?
Because you have more mass multiplied by the same amount of gravity.
Yep, exactly. Perfect. So, right, the way that I think about it is at the bottom, the hydrostatic pressure is what's forcing the water through the opening in the stopcock. And that hydrostatic pressure is higher when the column is taller, right? So we're going to have more pressure pushing the fluid through faster, and it'll gradually slow down as the stopcock drains. So let me turn this, and you guys can see if you're right. So I'm going to turn the stopcock, and you should see the fluid moving relatively quickly, but as time drags on and that hydrostatic pressure down here at the bottom gets lower and lower and lower, the rate at which this meniscus, this boundary between the liquid and the gas, moves starts to go down to the point where when we're down at 10 milliliters of fluid, it takes like a minute for the last 10 milliliters to leave the stopcock. So there you have it. I will collect the data and I'll post the data up on Canvas so that you guys can use the data to compare against your Bernoulli analysis. But I did want to show you guys that this is a burette, and this is what you guys will be working on for the first couple weeks of class. Okay, so as that drains, it's going to take a really long time now because the hydrostatic pressure is much lower. Can I answer any questions about just the demo experiment? Okay, so I'm going to let it drain. See, now it's really slow, right? It's like super slow. Okay, so seeing no questions. Sorry that we ran a little bit over, but I did want you guys to see that. So we'll stop recording and post this on Canvas.